Imagine a new dawn breaking, not on Earth, but on the desolate, ethereal landscape of the moon. A dawn powered not by the distant sun, but by something far more audacious. Something that hums with silent, immense power. We're talking about a nuclear reactor, planted firmly on lunar soil. By 2030, NASA plans to make this a reality, sparking a new, intense space race that will redefine humanity's place in the cosmos. Are you ready for humanity's next giant leap? Because it's powered by the atom, and it's happening sooner than you think. For decades, the moon has been a scientific playground, a celestial stepping stone. But for sustained human presence, for industry, for science that goes beyond fleeting missions, power is paramount. Solar panels, while effective during lunar day, fail entirely during the 2-week-long, brutally cold lunar night. Temperatures plummet to -173 degrees Celsius. Batteries simply aren't enough for the continuous operations we envision, extracting water ice, manufacturing tools, even growing food in future lunar habitats. We need something that offers constant, reliable energy, regardless of sunlight. We need something small, yet mighty. We need fission. Enter Project Fission Surface Power. This isn't just a concept, it's a rapidly developing initiative. NASA, in collaboration with the U.S. Department of Energy, DOE, and industry partners, is calling for proposals to design, develop, and deploy a small-scale, fission-based power system on the moon. The goal is clear: have a flight-ready system by the late 2020s, operational on the lunar surface by 2030. This isn't a massive, conventional nuclear plant. Think of it as a compact, robust power source, capable of generating up to 40 kilowatts of electricity, enough to power 30 average homes, but in a form factor small enough to be transported to another world. So how does this miniaturized marvel actually work? At its heart, it's remarkably similar to Earth-based nuclear power, but on a much smaller, safer scale. Uranium atoms are split in a process called fission, releasing tremendous amounts of heat. This heat is then converted into electricity. The key difference for lunar applications lies in its design. It's self-regulating, incredibly durable, and designed to operate autonomously for years without human intervention. Imagine a system engineered to withstand the vacuum of space, extreme temperature swings, and micrometeoroid impacts, all while continuously supplying vital energy. It's a testament to human ingenuity pushed to its absolute limits. Deploying a nuclear reactor on another celestial body isn't without its monumental challenges. First, radiation shielding. Protecting future astronauts and sensitive equipment is paramount. The current designs incorporate advanced materials and passive shielding techniques to minimize any risk. Second, heat rejection. In the vacuum of space, convection doesn't exist, making cooling extremely difficult. Innovative radiator systems, often large and unfolding, are crucial to dissipate excess heat. Third, launch and deployment. Ensuring the system survives the immense forces of a rocket launch and then deploys flawlessly on the moon is a feat of precision engineering. Each of these hurdles is being meticulously addressed, piece by painstaking piece, by some of the brightest minds on Earth. This nuclear ambition isn't an isolated project. It's a cornerstone of NASA's ambitious Artemis program, which aims to return humans to the moon by 2025 and establish a sustainable long-term presence. Think permanent lunar bases, scientific outposts, and even mining operations. Reliable power is the very foundation upon which these dreams will be built. The fission surface power system will not only support astronaut habitats, but also power in situ resource utilization, ISRU efforts, converting lunar soil into building materials, or extracting water ice for rocket fuel and life support. This isn't just about planting a flag. It's about building a sustainable lunar economy, a stepping stone to Mars and beyond. But NASA isn't alone in this pursuit of lunar power. The 21st century has ignited a new space race, with China and Russia making their own significant strides towards lunar dominance. China's ambitious change program has already seen multiple successful lunar landings and sample returns. They have openly declared plans to establish an International Lunar Research Station, ILRS, with Russia by 2035, aiming for a permanent human presence. While their specific power generation plans are less publicized than NASA's, it's clear they understand the critical role of robust, continuous energy. Imagine the strategic implications if one nation secures reliable, long-term power on the moon before others. This isn't just a scientific race, it's a geopolitical chess match playing out on the lunar frontier. Controlling key resources, like water ice and shadowed craters, and establishing a robust infrastructure, starting with power, grants immense strategic advantage. Imagine a future where lunar outposts become vital resupply points for deep space missions or even industrial hubs. The nation that masters long-term lunar habitation, powered reliably, will hold significant sway over humanity's expansion into the solar system. This isn't about claiming territory in the traditional sense, but about establishing influence, setting precedents, and leading the next era of space exploration. With nuclear technology comes an inherent responsibility for safety and strict regulation. On Earth, nuclear power plants are governed by incredibly stringent international protocols. How will this translate to the Moon? The Outer Space Treaty, signed by over 100 nations, dictates that space activities must be carried out for the benefit and in the interests of all countries. While it prohibits weapons of mass destruction in space, it doesn't explicitly detail regulations for lunar nuclear reactors. This raises complex questions. Who will regulate safety protocols? What international oversight will be in place? Ensuring transparency and international cooperation will be crucial to prevent any potential risks or conflicts as we venture further into the nuclear age of space. The applications of fission surface power extend far beyond our nearest celestial neighbor. Mars, with its thin atmosphere and even longer solar eclipses, would be an ideal candidate for similar nuclear power systems. Imagine self-sustaining Martian colonies, drilling for subsurface water, or powering advanced scientific instruments for decades. Further still, compact nuclear propulsion systems, derived from similar fission technology, could drastically cut travel times to the outer planets, making interstellar travel a more tangible dream. The Moon, in essence, becomes the ultimate testing ground, a cosmic laboratory for the technologies that will propel humanity throughout the solar system, and perhaps one day, to the stars themselves. So what does a nuclear reactor on the Moon mean for you, watching this right now? It means faster technological advancements here on Earth, driven by the intense demands of space. It means the birth of new industries, new jobs, and unprecedented scientific discoveries. It means a profound shift in humanity's self-perception, no longer confined to one planet, but truly becoming a multiplanetary species. The race for lunar power isn't just about kilowatts, it's about pushing the boundaries of what's possible, about igniting the human spirit of exploration, and about securing our future among the stars. Will we be spectators or participants in this bold new chapter? That thought is where our experiment ends for today. If this journey to a nuclear-powered moon sparked your imagination, help us fuel more explorations like this. Be sure to hit that like button, share this video with a fellow explorer, and subscribe to The Thought Experiment. Don't forget to ring that notification bell so you don't miss our next journey into the what-ifs of science and the future. And let us know in the comments below, do you think a nuclear reactor on the Moon is humanity's next giant leap, or a risk we're not ready for? Thanks for watching.